All right, how's it going, everybody? I am here making this video on Tuesday, April 20th, and today we're going to talk about section 11.3, the integral test and estimating sums. We have had our first two sections in chapter 11. We're on sequences and series, and what we're going to be discussing for most of the remainder of this chapter is judging the convergence of those sequences and series. Today we're going to look at judging the convergence of series, the sums. The sum of a sequence is a series. And what we're going to see is how integrals are related both with helping us determine do they converge or do they diverge. And if the series converges, we can also use integrals in a separate setting to help us judge an estimate as to what they converge to. So today is all about the integrals that are associated with series, which is not necessarily generally the case for most of this chapter right here. This is sort of like the most calculus that happens in this chapter until the final section of the chapter here. But today, again, we're going to get two different ways in which integration is associated to series. One, that integrals can help us determine does a series converge or not. Two, if a series converges, an integral can help us estimate what value it converges to. And very importantly, today we're going to see some really nice geometric pictures. I made some really nice stuff in Desmos that, in my opinion, is an excellent diagram to help us see what exactly is happening there. So, how can we use integrals to help judge whether a sum converges or diverges? And with the example that we'll look at today is let's determine if the series, right, of the sum 1 over n to the 1.2 converges or diverges. So we're adding up all terms that are of the form 1 over n to the 1.2 power. We know that the harmonic series, the series of summing terms of the form 1 over n, is going to diverge off to infinity. We saw that in the last video. We also know that 1 over n to the 1.2 will be smaller, right? You can see that all of the denominator terms are going to be larger, therefore the series overall will be smaller. But this is like our failed version of the comparison test right here. The harmonic series is large enough to diverge. We are interested in judging if this other series that we want to compare to it also converges or diverges, but we're smaller than a known divergent series. We could just be a smaller infinity, or we could be so much smaller that we actually are converging to a finite value. So the question is, this series is clearly smaller than the harmonic series, but we're not sure. Is it smaller enough to converge? I think it's weird how appropriate I think that verbalization is right there. In any event, we know it's smaller than a divergent series, but is it so much smaller that it converges, or is it just a smaller version of infinity? That's our struggle that we're kind of like trying to piece our way through here. So what I've made is I've made this really nice picture in Desmos, and I want to make some like arguments with you right now as to how we can use integration to judge the idea associated with this series right here. So let's go ahead and take a look at this link right here. Open that guy up. And here is what we can see. So here's this link, and I encourage you to follow this link as well and take a look at the things that I've gotten here. So here's what we've got. So a couple things. Let's kind of start with what we're seeing up here. One, the equation that you're seeing up top up here is exactly the equation representing the series of interest. So this black curve is giving, at its integer x values, is giving exactly the function value outputs that we're getting for the series, right? So when we do 1 over 1 to the 1.2, we get 1. When we do 2 to the 1.2 and take its reciprocal, we're going to get like 0.435. Now, the thing that you should notice is that we can make sort of an estimate of the size of this series by thinking about rectangles that we're adding up areas of. The reason why this makes sense is because when I'm computing the sum that's associated with this series right here, the first term, you should notice that the width of all of these rectangles is simply 1. So the height of each of these rectangles is the same as the area associated with each rectangle. The height of the rectangle is exactly the value of that particular term of the series, but the area we know to be tied to an integral. So the smart thing that we're doing right here is we're creating a graphical setting where we're creating rectangles. Since every rectangle is width 1, width times height is just going to give height every time for area. So in this diagram, height is equal to area because all the rectangles have width of 1. What this does for us is this allows us to make this translation between the height of the black curve and the area that's underneath these rectangles. And what you know is that this looks a whole lot like a Riemann diagram to you. It looks like we're doing some left-hand rule summation right here, right? So what we want to consider for ourselves is that right now, it seems like this black curve, if we were to integrate this black curve from 1 to infinity, it seems relatively obvious to me that we are going to get a number that is less than the overall value of the series, because the series value is equal to the area underneath all of these rectangles. The area underneath the rectangles is clearly an overestimate of the area underneath the curve, right? But I just said overestimate. I kind of phrased my comparison backwards right there. What we're trying to talk about is how much area is underneath the rectangles, and that's something that I don't know how to compute the sum for. However, we can see that the area underneath the rectangles is larger than the area underneath the associated curve, and I can do the integral to get that area underneath the curve. So this is where we are going to draw a Riemann diagram that is effectively representative of the terms that we're adding together in the series. We're going to come up with integrals that are going to represent associated areas that are either overestimates or underestimates. And by the way, you should notice that if we just shift all of our blocks over by 1, now our curve is a known overestimate for the series representation. And so it seems like just this shifting of our starting location by 1 unit is transitioning. Notice here, our rectangles here are all on the right-hand corners where they touch the curve, versus over here, our rectangles are all on the left-hand corners where they touch the curve. So this is literally like saying, it's basically like what we're thinking about today is we want to interpret our series as either being left or right hand Riemann sums, with delta x being 1 to make the area being equivalent to the value of the series. Then we want to compare them to their function equivalents so that we can use calculus to find the area underneath their function equivalents and make statements. Whereas, for example, in this scenario, as the diagram is right now, if I did the integral of 1 over x to the 1.2 from 1 to infinity, I would be getting a number that's guaranteed less than the value of the series. And alternatively, if I did the integral from -1 or excuse me, I guess it looks like starting the integral. So notice here, this is at a value where if we plug in, it looks like our diagram here starts at 1, right? So if our height at 1 is the first height that we're actually measuring right there, then we can do another integral right here where this is guaranteed to be an underestimate. Excuse me, the integral here is guaranteed to be an overestimate of the value of the sum, which is represented by the blocks that are sitting out here, right? So you should check out this graph, and I hope that this kind of helps you relate the idea of this value of the series as being estimated by the green and blue rectangles total area. We can estimate it or get bounds on it based on a related integral that is either clearly above or clearly below the rectangles that are of interest for our series that's out there. So let's go ahead and do the integral that should be associated with judging this convergence right here. So in this case right here, it seems to me like I know, based on the Desmos diagram, it should be the case that our integral from 1 to infinity should be greater than the series. And let's pop back there real quick, and I want to kind of confirm this. It looks like our series, right, we want to start judging our series at height 1 right here. So in this case right here, it seems like the integral from 1 to infinity is clearly going to be more than the value of the series going from 1 to infinity right here, because I can see that the black curve is clearly above the rectangles right here. So we're starting at 1 and going off to infinity, and I'm seeing we're clearly getting a larger overall value from the integral than we're actually getting from the series. So over here, I want to say from the Desmos diagram, is greater than so let's see if the integral converges. Now notice, based on the way we've set up this statement here, if this integral diverges, we again don't get any information about the series, because if we're smaller than a divergent series, I don't know if we're smaller as in finite or smaller as in just like a smaller version of infinity, right? So it has to be that this integral needs to converge, then we can conclude that the series must therefore also converge because it's even smaller, right? So if we do the integral over here, we can do this relatively easily, right? This is going to be the integral from 1 to infinity of x to the negative 1.2 dx. And so it seems like we're going to be getting here, let's see, I want to add 1 to the power, which gives me negative 0.2, which is 1/5, and we want to do 1 over that. So I'm in fact going to get 5x to the negative 0.2, evaluated from x equals 1 to x equals, well, okay, I'll write the bad thing right there. And now let's do this in terms of the, the proper notation for this guy right here. This should be 5 times the limit as b goes to infinity of x to the negative 0.2 from x equals 1 to x equals b. And that should be giving me 5 times the limit as b goes to infinity of b to the negative 0.2 and minus minus 1 to the negative 1.2. What we can see here is that since this is really a fraction, as b gets larger and larger, because this is a negative power, it's actually getting smaller and smaller. So we're getting 5 times 0 minus 1. And it seems like this is going to converge. Oh, wait, sorry. I'm realizing here, I dropped this, and I was like, we can get a negative value. When I did the integration right there, that should have been a negative on the constant of 5 right there. So we're getting 5. And so the integral converges to 5. So the integral converges to 5. The integral's area was clearly above the series area. So the series must also converge. Right? I've turned the summation argument into an area argument by expressing this series geometrically to look like that Riemann sum that we saw right there. So this idea right here is what we call the integral test. If we would like to judge if the series, right, generic phrasing for our series, the sum from n equals 1 to infinity of a sub n converges or diverges, that's what we'd like to do. If it is the case, so first restriction, we need to be able to write the series as a function. We saw in the previous couple videos that does not always happen. It needs to be the case that not only can we write it as the function, but the function itself, f of n, needs to be continuous, it needs to be positive, and it needs to be eventually decreasing. So it doesn't need to always be, it doesn't need to be a monotonic decreasing function, but we need to be able to go to some x value in the function where for all x values beyond that, it is decreasing. That's one of the requirements on 1 to infinity. If that's the case, then this series will converge if and only if the integral converges. So the if and only if means that that is a bidirectional statement. That means that we could actually use the integral test to use series to prove that integrals converge, and not just using integrals to prove that series converge. This goes if and only if means both directional. If one of these things is true, if A is true, then B is true, and if B is true, then A is true. That's what we get from if and only if right here. So we've got some requirements on here, but they're not too bad. So a couple notes about this. When we say eventually decreasing, and I already said this, we mean that there must be some special x value, we'll call capital N, such that for all the x values beyond capital N, f of x is decreasing. So that means you should be able to say to me, oh, if you go to x equals 486, past that, it's a strictly decreasing function. As long as you can come up with the location, x equals capital N, that's the location where beyond that we're decreasing, then that is an eventually decreasing function. 2. The lower bound of this sum and this integral can be values other than 1. They just need to match. So you should notice here, lower bound of 1 on the integral, lower bound of 1 on the sum. Those don't need to only be 1s. They can be any other number. As long as they match each other, then we're making a reasonable comparison here. 3. you might need to determine if a function is decreasing over the given interval to apply this test. If you can't show that this function is decreasing, then you shouldn't use this test. This test requires the function to be decreasing, so it might be the case that you need to stop for a moment and do the math and say, look, it's continuous. Look, it's positive. Look, it's eventually decreasing on this interval. Therefore, the integral test applies, and we can convert, and we can, conclude that it converges because I did the integration over here, right? So it might be that you need to do some math to show that the function is decreasing over the interval from a to infinity to apply this test. And you know how to do that because you've all taken Calc 1. So you are all capable of just taking the derivative and determining the sign of the derivative over the interval of interest. So it might be the case that you have a complicated function where you need to stop and do a smidge of calculus to prove that it's a decreasing function. Take that derivative and show that the sign is what you want it to be over the desired interval. That might be some math you have to do. Finally, we should never expect that the series value is the same as the integral value, and we saw this over here in Desmos. The area underneath the curve is not equal to the area underneath the rectangles, but knowing that one converges does tell us that the other converges. So the important thing here is that this is about the equality. I do expect, come on, Microsoft Word, be my friend today. I do expect that their convergence to match, but that is a categorical feature of the series and of the integral. I do not expect their actual value that they converge to be the same, given that they do converge. So don't expect their convergence, the value that they converge to be the same, but if one converges, then the other converges, as long as they meet these conditions that are going on up here. All right? So let's look at the most important conclusion from the integral test. Fortunately, this is something that we have already previously seen this semester. To get the most out of the integral test, we're interested in sums or series where we are unsure of convergence, but where we are able to compute the associated integral, right? So you should recognize that the integral test is only as useful as your ability to do the integration is, right? If we're given some terribly nasty function inside of a series describing the series, then the integral test probably isn't going to help us out, because if you can't integrate it, then you can't do the integral test, right? So that's one of our limitations here. So the integral test is useful when we can't just judge the series convergence alone, but where we could do the integration associated with the function equivalent. Fortunately for us, one of the major categories of scenarios in which that occurs is this P-series scenario that we have previously discussed when we looked at the comparison theorem back in 7.8, I want to say, was that? Chapter 7, Section 8, I think. And so now we're kind of revisiting this idea, as I promised we would back in whatever that section was. So let's look at the convergence of sums of the form 1 over n to the p power. And we want to say, if we know what p is, can we judge convergence or divergence? Remember that in the last video, we checked for the convergence of a geometric series of the form x to the n over 3 to the n, and we determined that this one parameter family of series converges when x was between -3 and +3. We referred to this as the interval or radius of convergence right there. I feel like I used the word radius, not interval. Similarly, we'd like to know for what values of p does this series 1 over n to the p converge? And you should notice that these are really similar things. I'm using n in a different context than I'm using n right here, whereas n is the exponentiation, whereas n is the base here. But we're sort of comparing here what's up with n versus what's up with p right here. So this is a pretty similar type of question. So since this 1 over x to the p function is continuous, as long as x is not equal to 0, but we're only interested in positive integer values of x, we know that it's decreasing because as x gets bigger and bigger and bigger, this is going to get to be smaller and smaller and smaller. And it's positive for, on the interval from 1 to infinity, we should be able to use the integral test to judge this guy. We already know that if p is equal to 1, then this is just the series of 1 over n. That's the harmonic series. We've already proven it diverges. We proved it twice in the last video. We just looked at p equals 1.2 in this setting right here, and we determined that it converged. So what about values on the other side of p equals 1? So let's just go ahead and do an example right here and say if p is equal to 0.8, does the series from n equals 1 to infinity of 1 over n to the 0.8 converge or diverge? Well, we can go ahead and check this with the integral test here. Let's do the integral from 1 to infinity of 1 over x to the 0.8 dx, which is really the integral from 1 to infinity of x to the negative 0.8 dx. I'm going to add 1 to the power and get 0.2, and 1 over 0.2 is now that positive 5, where I was supposed to be getting the negative last time when I made the mistake. This will be x to the positive 0.2 power, and this is what's getting evaluated from x equals 1. And again, I didn't leave enough room for me to write my limit statement, so I'll put those in quotes to recognize that I know that that's not legit. And this should be 5 times the limit as b goes to infinity of x to the 0.2, evaluated from x equals 1 to x equals b. This is going to give us 5 times the limit as b goes to infinity of b to the 0.2 minus b to the 1. Or sorry, nope, there's no b in the second part. I keep on trying to make the second part about b also. That's just 1 to the 0.2. And it looks like what we're getting here is 5 times infinity minus 1. It looks like this is going to diverge. Therefore, the series n equals 1 to the 1 over n to the 0.8 also diverges. Remember, the important thing happening up here when we stated this integral statement is this if and only if. The only way the series converges is if the integral also converges. The fact that the integral diverged means it's not possible for the series to converge, right? So we have determined that this series is going to diverge. So series of the form 1 over n to the p are referred to as p-series, and they're heavily used as comparisons throughout this chapter, throughout the usage with series in general. P-series are sort of like our most, the thing that we know for sure about, and they're easy to make comparisons to as sort of like a central location. By the observations that we've seen above, we could see exactly what we saw when we did this with integrals. The series 1 over n to the p will converge whenever p is greater than 1, and it will diverge whenever p is less than or equal to 1. And I think that you can see that even as we make p closer and closer and closer and closer to 1, we're always going to be getting b to a positive power right here. And when we let b go to infinity, it's always going to diverge off to infinity. On the other hand, if p is just barely bigger than 1, if p is 1.00001, we're still going to be getting things like a negative value on this guy right here, and therefore it's going to go to 0 as b goes off to infinity always. So I think that we can kind of make the non-formal argument here that we can definitely see by the math that we just did, and we can generalize our statements to converge when p is bigger than 1, diverge when p is less than or equal to 1, and the or equal to really matters right here. The equal to 1 is the harmonic series, and that's the one that we sort of know the most certainly is going to diverge right there. So this is the integral test, and as we said, there's two things that we want to do today. We want to say, can integrals help us judge if a series converges or diverges? We just did that. The answer is yes. The other thing we want to say is, if we know that a series converges, can we use integrals to help estimate the value that they converge to? And I think that the answer is going to again be yes, based on that same Desmos diagram. So let's go ahead and take a look at estimating some series. Suppose we would like to know the value of the series 1 over n cubed. Because it is a p-series, with p being 3, right? That's a p being 3. I know that this converges. This is essentially a result, a special result from the integral test is the p-series results, right? So I know all my classifications of all p-series because of the integral test. So indirectly, by way of the integral test, I know that this guy converges. I could just redo some of the integral I did up above right there. I know what result I'm going to get. What I want to do, though, is I know it converges to some number. I want to know what number does it converge to. So here's a way I can get an estimate. Since 1 over n cubed is a decreasing function, and it decreases quickly, most of the value of the series 1 over n cubed should occur in the early terms. So let's just add up a bunch of them. Let's just get a couple leading terms out there, right? So I'm going to denote our S sub n, our partial sum. All right, all right. I need to make this much more clear than I am right here. And this should just be 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed. And what I think I'm reasonable to say right here is that, oh, and let me back up a second. I did one wrong thing. I wrote that as S sub n. This should be S sub 5, the partial sum of the first 5 terms. And I think it's reasonable for me to say, therefore, that S sub 5 is approximately equal to the entire series. And the reason I feel pretty good saying that is because since this series, each term in this series decreases by so much when you go from one term to the next, I'm thinking even by 1 over 5 cubed, I mean, that's 1 over 125, right? So that's less than 0.01 right there. So whatever number we're converging to, I'm assuming that we got a bulk of the value from 1 plus 1/4 plus 1/27 is even like 0.04 right there. So I'm thinking we got like 1.3 in the first chunk of terms right here. And now every other term after that is adding like really, really, really small, negligibly small amounts. So it doesn't seem to me like we're going to be blowing up to any massive number out there. And so in this case, I'm just saying, I don't know, get the first 5 terms. Since this function decreases so quickly, just by looking at the first couple terms, you're getting a bulk of the value right away, right there. Um, but that's only looking at the first 5 terms. So what if I want to get a better estimate than this? This is exactly correct for what the first 5 terms are going to be like. And what I'm thinking to myself is maybe I can get an estimate of all terms after the 5th term by using some integral to get us some help, because I can only do the first few terms by hand, like like I don't even want to go to my calculator to get that, and that was only 5 terms right there. So here's my thoughts. If we know that a series converges, that certainly doesn't mean we can compute the value of the sum. However, we can use the same Desmos graphs to help us visualize how we might place upper and lower bounds on the value of the series. And so I allowed a note that I wanted to stick onto this thing to get separated from it right here. So I'm going to go ahead and maybe I'll do it like this. Here we go. And here's the thing that I want to do. I want to include a shifted version of our graph also to the Desmos graph. So let's go back to our Desmos graph and see if we can see some more things that remind us of Calc 1. So I'm going to go back to this graph over here, and importantly, I'm going to add a second function. We have defined the f of x function right here. What I'm going to do is I'm going to add a new expression. I'll put it right here, and I'm going to call this g of x, and I'm going to say it's equal to f of x minus 1. And what I want to do is slide this guy back over to here and see this. So here's what I'm seeing. It looks like in this case here, the black curve is an obvious underestimate of the value of the series. Remember, the value of the series is literally the area of the rectangles, whereas the red curve looks like it's an obvious overestimate of the value of the series. Furthermore, what I can see is that the discrepancy, the error amounts are large at the beginning, right? Look at all this chunk of green right here that the black curve missed out on. Look at all this chunk of white right here that the red curve missed out on, right? The errors are large early. But you should notice as we go later and later and later, the amount that we're off by, the errors out here are getting smaller and smaller and smaller. And this graph because I had to make these rectangles like one by one. That's why you're seeing the list of them over here. That's why I only went out as far as doing the first 5 of them. But you can imagine the further and further out we go, since this function's slope seems to be getting closer and closer to 0, the amount of error that our integral gives us relative to our series should be getting really, really small. Whereas it seems like there's potentially lots of error between the series and its integral at the beginning. So therefore, here was what I think my strategy should be. I think my strategy should be, let's compute the actual exact value of the series just for the first literal handful. When I say literal handful, I mean like maybe like 5 terms or something like that. That'll get us the exact answer for the first 5 terms. Then, For all the remaining area that we're supposed to be accumulating out here, what I can see is however much area is actually in the series, which remember is the area of the rectangles out here, it should be something between the area underneath the black curve and the area underneath the red curve, which are the integrals of the same function, just shifted over one step from one another, right there. Just starting accumulating their area at one function value off from one another right there. So they're very closely related integrals, and I can see the true value of the series lives between these two integrals right here. I can see the areas, right? So here's my strategy. Start off by getting something really close, by literally getting the exact value of the first couple terms. Then estimate the remaining area of the series by saying it's bounded in between two integrals. Then add the exact first couple terms to the boundedness of the between the two integrals for all the remaining infinite number of terms, and let's go ahead and call that our estimate. So let's go ahead and do this process here. So using integrals to estimate series. So this is just me talking through exactly that process that I just verbally described. To estimate the value of a convergent series, it doesn't even make sense to estimate the value of a non-convergent series, right? We can first compute the partial sum of the first n terms. So like our first 5 terms, that's getting us, we're exact so far. There's no estimate happening so far. Then we're going to estimate the remaining value as being bounded by an upper bound and a lower bound integral, exactly like we just saw in Desmos happening out there. We can write this inequality like this. This is our exact value we want, but can't get. Over here, what I'm seeing is because we're starting accumulating area one step later, this is a smaller integral than if we started collecting area at n. And so let me say that again. These two integrals have the exact same integrands of f of x, where f of x is the equivalent of a sub n. But this one doesn't start accumulating area until 1 unit later than this one does. Therefore, the area of this integral is less. Right? That's why it's part of the lower bound chunk over here. So this is our lower bound integral. And this is our upper bound integral. We can, again, I'm going to pop back over to Desmos. We can see these over here. Our lower bound integral is the black curve. Our upper bound integral is the red curve over here, because I can see that the red curve is overestimating and the blue curve is underestimating, but that their differences relative to the area underneath the rectangles is extreme at first, but I don't care because we're not using integrals at first. I'm saying that we're not going to let our integrals start being used until like 6 and beyond. We're letting 1, 2, 3, 4, and 5 be evaluated exactly, because I can do things like add 5 numbers. I can't add even like 500 numbers. That's too much. So I'm just getting an exact part for my first like 5-ish terms, then using the integrals to say it's between the area underneath the black and the red curves. And you can see the black and the red curves are basically like kind of converging on one another in the long run right there, saying the difference between them is going to be very, very small, and that's going to give us a good, nice, and tight estimate for our actual overall value of the series right there. Remember that S sub n is saying take the exact value of the first n terms, then add on our lower bound integral to get an overall lower bound estimate. Over here, we're going to get the exact value of the first n terms plus an upper bound estimate. This sum right here is saying take the first n terms and then take all the rest of the terms after that as well, right? This is like the S sub n plus, all the remaining actual exact values that are out there. You should notice that this g of x equals f of x minus 1 that we added to the graph translates into a new lower bound of f of n plus 1, and you should take a moment and realize that you agree with this statement right here. If I took the curve 1 over x squared and shifted it to the right by 1 unit, it becomes the graph of 1 over x minus 1 squared. Therefore, if we start accumulating area for this guy at 2, 2 is 1 unit to the right of 1. So these two integrals should certainly be giving us the exact same area. This value on the left is the exact same expression as the value on the right, just everything on the left has been shifted to the right by 1. But because I shifted the function to the right by 1, but also started accumulating area 1 unit further to the right, it's really representative of the exact same areas that we're interested in right here. So this is just the adjustment that we made. That's why you're seeing that I didn't make my adjustment inside the integrand for the new function. I instead made my adjustment of the bounds of integration as to where did we start accumulating these. What you know is that when we do our left and our right hand Riemann sums, it's sort of like we start either at a sub 0 or at a sub 0 plus delta x. It's like that the next subinterval that we start at accumulating for the right hand sum versus the left hand sum, stuff like that. That's exactly what you're seeing. This is the integration version of right hand versus left hand sums, upper bounds and lower bounds, stuff like that from our Riemann sums. All right. Now, we're just going to use some notation right here. This next statement here is just using some notation. So now I'm going to say, if we define the remainder to be the difference between the partial sum and the series sum, which is actually just S. So I'm saying here, R sub n equals, take the entire series and subtract off the partial sum of the first n terms. So this is like the tail. It's the remaining parts that we didn't get in our exact value computation for the first partial sum of the first like 5-ish terms. And so all I'm going to do is I'm just going to subtract S sub n from all of my terms. Well, you can see from all three sides of this inequality. So I've got the screen scrolled in a funky spot. So you can see that subtracting S sub n from the left and the right just eliminates them. So we just get the integral on the left and the right. We can see that subtracting off the S sub n from the series itself down here is just giving us that remaining tails area, right? So this is the tail area should be between these two integrals. Let me write this here. Right. So the use of these inequalities still requires our restriction that f of x be continuous, positive, and decreasing on that subinterval. Notice that this subinterval is now from n off to infinity, because that's where our first integral starts right there. But given that, we can use this to bound the tail of any of our series of this form. So let's do this to estimate the value of the sum of 1 over n squared by computing the first 5 terms exactly and using integrals to bound the 6th term and beyond, and combining that information to get an interval in which we think the value of this series lives. And then I'll tell you the exact value, which I don't know how to actually get myself. I just know this one because I've seen this one crop up so many times, and we'll see that we did a pretty dang good job. So we want to first get our S sub n being n sub 5, or with n is 5. S sub 5 is the sum from n equals 1 to 5. It's the first 5 terms of 1 over n squared. So that should be 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25, right? That's the first 1 over n squared 5 terms right there. If we go ahead and throw this guy into a calculator, which I already did just because I didn't want to sit here and do calculator business today, 1.4636111, and then some more terms out there. And remember, I'm trying to keep a lot of decimals here. I'm trying to estimate an infinite series that's converging to a value that looks already to me like it's probably going to be a number less than 2. I don't think, again, my next term is 1 over 36. That's less than 0.03. We're not exactly contributing a lot anymore. A bulk of the contributions are getting made in the first 5 terms because this is a decreasing series out there. So now let's get integral bounds for the tail beyond n equals 5. Sorry, I want to phrase this differently. I feel like the way I was going to phrase that made it sound like I was looking for bounds of integration. I'm looking to bound the value of the series using our integrals, our upper and lower bound integrals. So we're saying here that we should be looking at this n plus 1. We're letting n be equal to 5, so it should be that 6 is the lower bound of our integral for the lower bound of the tail of the series, and our lower bound of the integral should be 5 for the upper bound of the tail of the series. It's kind of tough verbally. There's two different bounds that we're seeing out there. So, what? So what I'm saying here is that the integral from 6 to infinity of 1 over x squared dx is less than the remainder from 5 on is less than the integral from 5 to infinity of 1 over x squared dx. This is my upper bound and lower bound integral right here. It looks like both these integrals are the same. They just have different bounds of integration. So I'm going to just go ahead and like kind of pick a parameter for this guy right here. I'm just going to say is the integral from a to infinity of 1 over x squared dx is the integral from a to infinity of of x to the negative 2. I'm going to add 1 to the power to get negative 1. So this should be negative x to the negative 1, evaluated from x equals a to x equals infinity, in quotes, because I keep forgetting to do my notation right here. Negative limit as b goes to infinity of x to the negative 1, evaluated from x equals a to x equals b. And this should be giving us negative limit as b goes to infinity of b to the negative 1 minus a to the negative 1. And it looks like here this is going to be giving us negative. As b gets infinitely large, the negative 1 power is going to go to 0. So it looks like we're getting 1/5 and 1/6. 1/6 for the lower bound version, 1/5 for the upper bound version. So now I think I can go back to writing my inequality from above right here. It looks like we can now return to our, let's see, integral of 6 to infinity of 1 over x squared dx. Well, that gave me just 1/6. This gave me 1/5. And so now what I can go ahead and do is that's my tail from 5 to infinity. Oops. So now let's get those first 5 terms in there. And by the way, I think that what I meant to say was a parenthesis right there, meaning that this actually started at 6. Oh, and I want to keep going back because I wrote n's in here where I wanted 5s. Oh my gosh, can't write out the last of this here. S sub 5 plus 1/5. And the whole point of this is that this is actually the series. This says add the first 5 terms to all the terms after the 5th term. Well, that gives us the whole dang series right here. So this is going to be giving me our, we already estimated what S5 was right there. That's our S5 estimate. And so if we go ahead and we throw these into the calculator now, I'm getting 1.630278 is less than, this is the entire series from n equals 1 to infinity of 1 over n squared, and this is 1.663611. All right, so here is our estimate of the value of the series by exactly computing the first 5 terms and then estimating the remaining infinite number of terms as being bounded in between 2 integrals right there. And very excitingly, the actual value of the series, this is the sum of 1 over n squared from n equals 1 to infinity, It turns out that it can be proven that you will get exactly pi squared over 6 from this guy, which has a decimal expansion of 1.64493. So you should notice that we did get something that is very nicely in between our two bounds right here that we came up with, proving that this series actually converges to pi squared over 6. I don't know how that happens. I think that's especially weird because, I don't know, pi cropping up in weird scenarios is weird like this because pi is a ratio. It's a geometric ratio, but here it seems to be something that we're getting out of counting things, which seems very odd to me. Um, very odd to me. But in any of, and especially at a pi squared, that makes me think about areas. So now maybe this makes me think, man, maybe our geometric idea in Desmos is a really great idea because pi squared says to me something like area of a circle is somehow involved in that series right there. Um, hmm, hmm. That's interesting. So in any event, this is our good technique for estimating the values of known convergent series is to say the bulk of the value should be in the first couple terms. So with this one, we arbitrarily picked five terms to get the exact value of. Then we estimated the value of the sixth term off to infinity with an upper bound and lower bound integral, just like our left and right Riemann sums is all we really did. We said the tails, this is all of our tail stuff. Then we added on the first five terms to get the overall stuff down here at the bottom. And this we can see, it's known that this is a good bound on the actual value of that series right there. So here's the integral test, an estimating series with integrals. This is really some of the only calculus we're doing in the first big chunk of this chapter out here. So you're welcome for the nice and short video here today. And what you can see is that next week we're going to hit it big with some big topics here. 11.4, 11.5, 11.6. We're going to look at the comparison test, the ratio and root test. We're going to see rules for absolute convergence when we're talking about convergence of absolute values of series. We're going to look at alternating series, which are going to do some really funky things to us. Alternating series meaning we get positives and negatives alternating back and forth with the signs. We're going to see some pretty funky stuff pop out from some of our alternating series things out there. So we're going to hit 3 sections next week. We're going to try and combine some things. It really does kind of matter that we get to sections 11.11 and 11.12, but we only have 2 weeks of content left. So it's certainly the case that we're going to kind of trim the fat a little bit right here and kind of hit just the highlights of most of these sections remaining in chapter 11, but they're all going to keep on giving us this broad overview of how do we judge what we know about series, how can we use other pieces of math to know about it. And I do want to just say one last time, it really does matter that we wrap this up. I have already written the homework assignment for section 11.12, so I promise we will be getting to talking about Taylor series. It is one of the most important things that we arrive at the end of this because it is going to, I promise you that every math class you'll take from now on will bring up Taylor series, so it matters that we get to that point in this textbook right here. So we are going to kind of power through chapter 11 in the next couple of weeks, but I'm not going to, it's not like we're going to talk every single down and dirty detail of every single section though, but we are going to kind of take a hot lap through chapter 11 here to wrap these things up. So I will see you guys next week in sections 11, 4, 5, and 6 to look at a whole bunch more tests that we can do to judge the convergence of sequences and series. I will see you guys then. Have a good one.